Good day, students. Today, we're embarking on a fascinating journey through the realm of solid materials and their pivotal role in modern technologies. Imagine a world where the materials we use in everyday technologies are mostly solids. From magnets that power airplane turbines to semiconductors that form the heart of solar cells and LEDs, and even polymers that safeguard our products and find applications in biomedicine. But have you ever wondered how these incredible materials come to be? Well, that's where chemists come into play. They're the driving force behind discovering new materials and finding innovative ways to process natural substances, transforming them into materials with remarkable properties. These properties can range from electrical and magnetic traits to optical, catalytic, and mechanical qualities. Now, let's delve deeper into the captivating realm of solid materials, exploring their structures and the incredible role they play in shaping our technological landscape. Good day, students. Welcome back, eager minds. Today, let's focus on the incredible contributions of chemists to the development of materials that power our world. Picture this. Chemists are like wizards, conjuring up new substances that didn't even exist before. They're the masterminds behind inventing novel materials that hold unique qualities. But that's not all. Chemists are also the architects of change. They have the power to process natural materials in ways that transform them into substances with specific properties. Imagine turning a mundane material into something with exceptional electrical, magnetic, optical, catalytic, or mechanical traits. These chemically engineered materials form the backbone of our technology-driven society. Now, let's dive into the nitty-gritty of solid materials and explore their structures and mesmerizing properties. Welcome back. Greetings, inquisitive minds. Let's take a closer look at how solid materials shape the technologies we rely on every day. First up, alloys, a blend of different metals that create materials with exceptional magnetic properties. These alloys play a vital role in crafting magnets that power airplane turbines and a multitude of other devices. Next, we have semiconductors, the unsung heroes behind solar cells and light-emitting diodes, LEDs. They have the magical ability to conduct electricity but not too much, perfect for harnessing solar energy and creating light sources. And let's not forget polymers, versatile materials used in packaging and biomedical applications. These substances provide us with materials that are both functional and safe. As we uncover these applications, remember that each of these solid materials has a unique story to tell, and they all contribute to the intricate tapestry of technology that surrounds us. Greetings. Hello again, eager learners. Let's conclude our exploration by pondering the future that chemistry unlocks for us. With every passing day, chemists are on a quest to unveil new materials that push the boundaries of what we thought was possible. They're the pioneers who fuel innovation by creating substances with unprecedented properties. Imagine materials that are lighter, stronger, more efficient, and capable of performing tasks we can't even dream of yet. These discoveries propel us forward, enabling groundbreaking advancements across industries. So, as you continue your journey of learning, remember that you're not just studying chemistry or materials. You're gaining insights into the very essence of our technological future. Hello again. Good day, students. Today, we're embarking on an exciting journey into the realm of solid-state chemistry. By the end of this section, you'll have a solid grasp of various concepts that govern the properties of solids. Our objectives include understanding how different types of bonding influence physical properties, differentiating between crystalline and amorphous solids, and delving into the intricate world of crystal lattices. So, let's dive in. Good day, students. To begin, let's delve into the classification of solids, based on their bonding and intermolecular forces. We have four main categories: ionic, covalent, metallic, and molecular solids. The type of bonding greatly impacts the physical properties of these solids. For example, ionic solids tend to have high melting points due to strong electrostatic forces, while molecular solids generally have lower melting points due to weaker intermolecular forces. Remember, these bonds shape the properties we observe. To begin, as we journey forward, It's essential to distinguish between two key types of solids: crystalline and amorphous. Crystalline solids exhibit an orderly, repeating pattern at the atomic level, which leads to distinct melting points. On the other hand, amorphous solids lack a well-defined structure, resulting in a gradual softening over a temperature range, rather than a specific melting point. Keep this in mind as we explore the world of solid structures. As we journey forward, let's get into the nitty-gritty of lattice points and arrangements. Lattice points are the positions within a crystal lattice where atoms or molecules are located. In the body-centered cubic (BCC) lattice, atoms exist at the lattice points and also at the center of the unit cell. In contrast, the face-centered cubic (FCC) lattice boasts atoms not only at the lattice points but also at the center of each face. This intricate arrangement plays a crucial role in defining the properties and behavior of various solids. Let's get into the Welcome, dear students. Today, we're delving into the captivating realm of solids and their intriguing properties. Our journey kicks off by exploring the remarkable diversity present in solids. Imagine solids that are as hard as diamonds and yet others that are as soft as wax. Some solids conduct electricity with ease, while others remain insulators. It's fascinating how the malleability of certain solids contrasts with the brittleness of others, making them resistant to shape changes. What's the secret behind these distinctive properties, you ask? Well, it all boils down to the atomic bonds that hold their constituent atoms together. These bonds play a crucial role in dictating both the physical attributes and the structures of solids. As we embark on this exciting journey, remember that we can classify solids based on the types of bonds they possess. Let's dive deeper into the world of solid properties and bond classifications. Welcome, dear Hello again, curious minds. Now that we're getting into the nitty-gritty, let's explore the various types of atomic bonds that give rise to the diverse properties of solids. First up, we have ionic bonds. In these bonds, electrons are transferred from one atom to another, creating charged ions that are held together by electrostatic forces. Next, covalent bonds enter the spotlight. Here, atoms share electron pairs, creating strong connections. Metallic bonds, on the other hand, involve a sea of delocalized electrons that contribute to the strong bonding observed in metals. And let's not forget about intermolecular forces, which play a vital role in molecular solids. These forces arise due to the interactions between molecules and contribute to properties like melting and boiling points. Remember, each bond type shapes the solid's behavior in its own unique way. Let's press on and uncover more about the intricate world of solid bonds. Hello again. Great job, students. Now that we've unraveled the bond types, let's see how they influence the properties we observe in solids. Ionic bonds, known for their electron transfer, contribute to solids with high melting points, due to the strong electrostatic attraction between ions. Covalent bonds, which involve shared electrons, result in solids with strong, directional bonds that lend them their hardness. Metallic bonds, with their sea of mobile electrons, lead to excellent electrical conductivity and malleability. As for intermolecular forces, these subtle interactions impact the volatility of molecular solids, affecting their phase transitions. It's truly mesmerizing to see how the atomic-level connections shape the macroscopic properties we observe. Let's keep our curiosity burning as we explore further. Great job, student! Wonderful insights, everyone! Now, let's organize our understanding by classifying solids according to the types of bonds they exhibit. First, we have ionic solids. These solids boast well-ordered arrangements of ions, and their properties are influenced by the strength of their ionic bonds. Next up are covalent network solids. These structures consist of repeating covalent bonds, forming intricate networks. Metallic solids, as we learned earlier, feature the free movement of electrons, contributing to their conductivity. And then there are molecular solids, where intermolecular forces dominate and hold the molecules together. It's like sorting solids into different families, based on their atomic connections. Isn't it fascinating how these classifications help us make sense of the solid world around us? Let's continue our captivating journey into the captivating universe of solid properties and bonds. Wonderful insight! Welcome back, everyone. In our exploration of different types of solids and their unique bonding, we begin with metallic solids. These remarkable solids are held together by a sea of valence electrons shared collectively among the atoms. This distinctive bonding allows metals to conduct electricity and provides them with strength without brittleness. Now, let's dive into ionic solids. In this case, the bonding arises from the electrostatic attraction between positively charged cations and negatively charged anions. This bonding leads to the brittleness and poor electrical conductivity often observed in ionic solids. Moving on to covalent network solids, their structure is defined by an extensive network of covalent bonds. This bonding configuration results in materials with exceptional hardness, such as diamond, and is responsible for the unique properties found in semiconductors. Our journey doesn't stop here. Molecular solids, our last category, form due to intermolecular forces like dispersion forces, dipole-dipole interactions, and hydrogen bonds. These forces are relatively weak, resulting in soft materials with low melting points. Now, let's dig even deeper into the characteristics of these fascinating types of solids. Welcome back, everyone. Great to see you all engaged. Let's focus on metallic bonding and its intriguing properties. Imagine a sea of valence electrons that are collectively shared among the metal atoms. These electrons aren't bound to any specific atom. Instead, they move freely throughout the structure. This unique arrangement allows metals to conduct electricity efficiently, as electrons can easily flow. Moreover, this delocalized electron cloud contributes to the strength of metals while maintaining malleability, ensuring they don't shatter like glass. The next time you see a shiny piece of metal, remember the dynamic dance of these electrons. Great to see you all. Welcome, students. Are you all ready for some electrifying knowledge? Today, we're going to dive into the fascinating world of ionic bonding. So, let's imagine positive cations and negative anions coming together in a lattice structure. This intricate arrangement is held together by the captivating force of electrostatic attraction. Now, pay close attention. This ordered structure is what makes many ionic solids appear brittle. When an external force is applied, something interesting happens. The like charges in the lattice align and repel each other. This repulsion, my dear students, is what causes the solid to break. But remember, it's not all about brittleness. This unique bonding style also plays a crucial role in stability. However, there's a trade-off. This arrangement, while providing stability, actually hinders the flow of electrons. This limitation results in poor electrical conductivity. So, here's a thought to ponder upon. The next time you hold a piece of salt in your hand, I want you to think about the intricate dance happening between those charged particles. That's all for today's lesson. I hope you found this both enlightening and inspiring. Until next time, keep exploring and learning. Welcome, student. Fascinating stuff, isn't it? Let's shift our focus to covalent network solids. In these solids, atoms are interconnected by an extended network of covalent bonds, creating a robust structure. This bonding type is the strongest and contributes to extreme hardness in materials like diamond. Just imagine, the carbon atoms in diamond are held together by this strong network, making it one of the hardest known substances on Earth. As we continue, you'll see how this type of bonding also plays a pivotal role in the world of semiconductors. Fascinating stuff. Fantastic job following along. Now, let's uncover the secrets of molecular solids. These solids are formed when molecules are held together by intermolecular forces, which are relatively weak compared to covalent or ionic bonds. These forces, like dispersion forces, dipole-dipole interactions, and hydrogen bonds, arise due to temporary charge imbalances or the polarity of molecules. As a result of these weaker forces, molecular solids tend to be soft and have lower melting points. Think of substances like ice or sugar, which demonstrate these characteristics. The dance of these intermolecular forces shapes the properties we observe in these materials. Fantastic job! Bravo, everyone! We've taken an incredible journey through the various types of solids, and their bonding. Remember, each type, metallic, ionic, covalent network, and molecular, offers a unique set of properties. Metallic solids shine with their delocalized electrons and electrical conductivity, while ionic solids stand out for their brittleness and fixed ions. Covalent network solids bring us extreme hardness and fascinating semiconducting properties. Finally, molecular solids, held together by relatively weak intermolecular forces, provide us with softness and lower melting points. As you move forward, connect these concepts to the world around you, and keep exploring the wonders of chemistry and materials. Bravo, everyone! Welcome back, eager minds. Today, let's focus on the incredible contributions of chemists to the development of materials that power our world. Picture this. Chemists are like wizards, conjuring up new substances that didn't even exist before. They're the masterminds behind inventing novel materials that hold unique qualities. But that's not all. Chemists are also the architects of change. They have the power to process natural materials in ways that transform them into substances with specific properties. Imagine turning a mundane material into something with exceptional electrical, magnetic, optical, catalytic, or mechanical traits. These chemically engineered materials form the backbone of our technology-driven society. Now, let's dive into the nitty-gritty of solid materials and explore their structures and mesmerizing properties. Welcome back. Hello again, students. Our fascinating journey continues with a focus on nanomaterials, a truly unique category of solids. These solids have captivated scientists and engineers due to their extraordinary properties that emerge from their tiny crystal dimensions. When we talk about nanomaterials, we're referring to solids whose individual crystals have been shrunk to the range of 1 to 100 nanometers. Yes, that's incredibly small. But don't be fooled by their size. Nanomaterials exhibit remarkable changes in their properties. Even conventional materials we're familiar with can showcase entirely different behaviors at the nanoscale. Imagine the possibilities that arise when we manipulate materials at such a minuscule level. Stay curious as we journey further into the world of unconventional solids. Hello again, Hello, dear students. Today, we're stepping into the intriguing realm of crystalline and amorphous solids. Now, let's start by acknowledging the remarkable nature of solids, which contain an immense number of atoms. For instance, consider a 1-carat diamond, and you might be amazed to learn that within its mere 57 m³ volume, there are approximately 1.0 times 10 to the 22 carbon atoms. But how can we possibly wrap our minds around describing such a colossal assembly of atoms? Well, here's the exciting part. Many solids exhibit structures with repeating patterns that extend in all 3 dimensions. Think of it as if you're stacking countless identical building blocks to form a solid, much like constructing a wall with identical bricks. These patterns are the key to understanding the properties of various solids, and they allow us to explore 2 main categories: crystalline and amorphous solids. So, let's dive deeper into these intriguing distinctions. Hello, dear students. Alright, everyone, let's move on to topic number 4. On this topic, we'll be discussing amorphous solids and their intriguing lack of regular patterns. Amorphous solids are defined as materials that lack a distinct, long-range order in their atomic arrangement. Unlike their crystalline counterparts, these substances don't have a well-defined repeating structure. This absence of a consistent arrangement gives rise to a variety of physical properties that can differ significantly from crystalline materials. Let's consider a few examples of amorphous substances: glass, rubber, and some plastics. Now, I'd like to emphasize the variability in these physical properties. Due to the lack of a well-ordered structure, amorphous solids can display a wide range of characteristics. For a visual aid, take a look at the image on the topic. It depicts the amorphous solid structure we've been discussing. So, to sum up, amorphous solids are defined by their lack of a regular atomic arrangement. This leads to diverse physical properties, and examples like glass and rubber showcase this concept well. Alright, that wraps up our discussion of amorphous solids for this topic. Take a moment to absorb the information, and feel free to ask any questions before we move forward. Alright, Now, let's move on to topic number 5. Here, we'll be delving into the applications and significance of solid structures. As we explore this topic, pay close attention to how crystalline structures play a pivotal role in electronics. Furthermore, you'll discover the presence of amorphous solids in everyday objects around us. But what truly stands out is the intriguing concept of tuning properties through precise structure control. This, in turn, has a substantial impact on the overall functionality of materials. Now, as you focus your attention on the topic, you'll notice an accompanying illustration demonstrating an electronic circuit. Remember, understanding the applications and significance of solid structures can provide invaluable insights into the realm of materials and their potential. Take a moment to absorb this information, and when you're ready, we'll move forward to the next intriguing aspect of our study. Now, let's move. Hello, dear students. Today, we're embarking on an exciting journey into the realm of crystalline solids. These remarkable substances have a unique property. Their atoms are arranged in an orderly repeating pattern. Imagine them as tiny building blocks forming a well-organized structure. This arrangement gives rise to flat surfaces, also known as faces, which have specific angles between them. This results in the creation of highly regular shapes, almost like nature's geometric puzzles. Let's take a look at some well-known examples of crystalline solids before delving deeper. Hello, dear. Welcome back, students. Now, let's explore the concept of crystal faces and angles in more detail. The distinct faces on crystalline solids are a direct result of how their atoms are structured. These faces exhibit specific angles between them, and these angles are quite consistent for a given substance. In fact, these characteristic angles are a unique fingerprint of the material. It's truly remarkable how the internal arrangement of atoms influences the external appearance of the crystal. As we move forward, keep in mind how these geometric characteristics play a crucial role in identifying and understanding crystalline solids. Welcome back. Hello again, young scholars. Now, let's shine a spotlight on some noteworthy examples of crystalline solids. First up, we have sodium chloride, commonly known as table salt. Its crystal structure forms a cube with the atoms arranged in a neat pattern. Next, say hello to quartz, a mineral with a hexagonal prism shape due to its atomic arrangement. And let's not forget about diamond, the gem that dazzles with its exceptional brilliance. Its crystalline structure involves a tetrahedral arrangement of carbon atoms. Can you imagine the intricate dance of atoms that gives rise to these beautiful forms? Let's press on to discover more about the captivating world of crystalline solids. Hello again, young. Welcome back, students. Today, we're delving into a captivating topic: amorphous solids. These intriguing materials are named for their lack of a distinct crystalline structure. Their atomic arrangement lacks the meticulous order we find in crystalline solids. At the atomic level, amorphous solids share similarities with liquids, but here's the twist. The molecules, atoms, and ions within them don't enjoy the same freedom of movement as they do in liquids. Unlike crystals with their well-defined faces and shapes, amorphous solids display a more irregular and random arrangement. Let's take a closer look at some familiar examples of amorphous solids: rubber, glass, and obsidian, which is volcanic glass. These materials might not have the rigid structure of crystals, but they're still vital components of our world with unique properties. Now, let's continue our journey by exploring the intricate nature of amorphous solids further. Welcome back, students. Hello again, dear students. Let's dive deeper into the atomic realm of amorphous solids. Picture this. The atomic structure of amorphous solids is akin to that of liquids, but there's a catch. The molecules, atoms, and ions within amorphous solids experience restricted movement. They don't enjoy the same freedom seen in liquids. This lack of mobility greatly influences the behavior and properties of these materials. Imagine how this difference in atomic arrangement affects the mechanical, electrical, and thermal properties of amorphous solids. Understanding this distinction is crucial as it sheds light on why amorphous solids possess their unique characteristics. Now, let's move on to our next segment, where we'll uncover even more about the fascinating world of amorphous solids. Hello again. Great job, students! Now, let's explore the practical side of amorphous solids. These materials might lack the perfect order of crystals, but they're far from ordinary. Amorphous solids boast a range of versatile properties that find applications in diverse industries. Consider the world of glassmaking, where amorphous solids like glass are shaped into intricate forms for windows, containers, and even smartphone screens. Packaging materials also benefit from their unique characteristics. In the realm of electronics, amorphous solids play a crucial role due to their non-crystalline nature. One interesting phenomenon we encounter is the amorphous to crystalline transition. This occurs through controlled cooling, and it can significantly impact the material's properties. So, the next time you're looking through a glass window or using your smartphone, remember the fascinating world of amorphous solids that makes it all possible. Stay curious as we journey deeper into the realm of materials. Great job, student! Bravo, dear students, on your attentive journey through the realm of amorphous solids. Today, we explored the intriguing world of materials that lack crystalline order, yet possess remarkable properties. We learned that despite their seemingly chaotic structure, amorphous solids find their place in glassmaking, packaging, and electronics. The amorphous to crystalline transition added another layer of complexity to our understanding. As we conclude this session, I encourage you to continue exploring the exciting field of material science. Remember, our world is rich with hidden wonders waiting to be unraveled through curiosity and inquiry. Until our next class, keep your minds open and your thirst for knowledge alive. Thank you, and see you soon. Bravo, dear. Welcome back, students. Our exploration continues with a closer look at unit cells, the fundamental building blocks of crystalline solids. Think of unit cells as the smallest puzzle piece that repeats throughout the crystal. They're like the DNA of the crystal structure. A single unit cell encapsulates the entire arrangement of atoms present in the solid. Depending on the crystal system, unit cells can take on different shapes and sizes. These variations play a crucial role in determining the overall properties of the crystal. Let's proceed to unravel more about the intricacies of unit cells and their significance. Welcome back, students. Great job, everyone! Now that we're familiar with the concept of unit cells, let's explore the arrangement of atoms within these units. Imagine the atoms as guests attending a grand ball within the unit cell. The positions of these atoms are meticulously defined, and this arrangement contributes to the crystal's unique structure. From simple arrangements to more intricate ones, the atoms within the unit cell play a crucial role in shaping the overall crystal lattice. As we delve further, you'll see how this atom arrangement influences the properties of different crystals. Great job, everyone! Welcome to an exciting phase of our journey, students. Now that we comprehend unit cells and their atom arrangement, let's explore how these building blocks come together to create the mesmerizing crystal lattice. Imagine a skyscraper built by stacking identical floors. In a similar manner, crystal lattices are constructed by stacking unit cells in a repeating pattern, extending in all three dimensions. This organized repetition gives rise to the crystal's well-defined structure. As we wrap up today's exploration, remember that the combination of unit cells and their arrangement forms the backbone of a crystal's remarkable properties. Welcome to You're doing wonderfully, students. Before we conclude, let's reflect on how the concept of unit cells intertwines with the properties of crystals. The size and arrangement of unit cells have a direct impact on a crystal's characteristics. Think of it like the arrangement of ingredients in a recipe affecting the taste of the final dish. Different unit cell sizes and arrangements lead to varying properties such as optical, electrical, and mechanical traits. As we bid farewell to this topic, remember that our exploration of unit cells and crystal lattices is a stepping stone into the captivating realm of materials science and the intriguing world of solid-state structures. You're doing wonderful. Hello again, students. Today, we're delving deeper into the captivating world of crystals and their intricate arrangement. Our next stop is the concept of a crystal lattice. Imagine this lattice as a geometrical pattern of points that acts as a foundation for the entire crystal structure. This lattice is like an abstract scaffolding, not physically real, but incredibly important in understanding the arrangement of atoms in a crystal. Picture this. We can construct the entire crystal structure by first creating this scaffolding, the crystal lattice, and then filling each unit cell with identical atoms or groups of atoms. It's like putting together a puzzle where the pieces are these repeating unit cells. Ready to learn more? Let's move on. Hello again, Hello, bright minds. Now, let's explore the transition from the abstract to the tangible. We've introduced the concept of the crystal lattice as an abstract framework. But how does this framework transform into a real crystal structure? Well, the lattice serves as our guiding star. Think of it as the blueprint that outlines where each unit cell should be placed. The unit cells, in turn, are like the building blocks, each accommodating identical atoms or groups. As we meticulously place these atoms within the unit cells according to the lattice's instructions, the crystal structure emerges, layer by layer. It's a process that transforms an abstract concept into a remarkable reality. Hello, bright minds. Great job, attentive learners! Before we conclude, let's recap the key points we've explored today. We delved into the concept of a crystal lattice, that intricate arrangement of points that sets the stage for the crystal structure. This lattice serves as an abstract guide, directing us in placing unit cells, the essential building blocks, within it. Inside these unit cells, identical atoms or groups form patterns that repeat throughout the crystal. Our journey takes us from the abstract lattice to the tangible crystal structure, where atoms find their precise spots according to the lattice's plan. So, remember, every crystal's beauty and functionality stem from this captivating dance of atoms within their lattice-defined homes. Great job, Hello, dear students. Today, we're about to embark on an exciting journey into the realm of crystal lattices. Before we delve into the intricate structures of solids, it's crucial to grasp the properties of these crystal lattices. To ease into this topic, we'll begin by exploring two-dimensional lattices, which are more straightforward to visualize compared to their three-dimensional counterparts. Just like a puzzle, crystal lattices are made up of repeating units. Let's take a look at Figure 1.2, which displays a two-dimensional array of lattice points. Each of these lattice points shares the same surroundings, creating a sense of uniformity. The positions of these lattice points are precisely defined by what we call lattice vectors, A and B. Now, imagine starting from one lattice point and using the lattice vectors to reach any other point on the lattice by adding whole number multiples of these vectors. This foundational concept will serve as the cornerstone for our exploration of crystal lattice structures. So, let's dive into the intricacies of two-dimensional lattices and set the stage for our study of solids. Hello, dear Welcome back, everyone. As we venture further into the world of crystal lattices, let's solidify our understanding of their properties. Imagine a beautifully intricate pattern formed by the arrangement of lattice points. This arrangement repeats itself, much like a mesmerizing mosaic. It's important to note that every single lattice point experiences an identical environment, a key characteristic of crystal lattices. To navigate through this lattice world, we rely on lattice vectors, A and B. These vectors define the positions of the lattice points and guide us in moving from one lattice point to another. Here's an intriguing thought. Starting from any lattice point, you can seamlessly travel to any other point on the lattice by skillfully adding whole number multiples of the lattice vectors. This mathematical dance of vector addition allows us to explore the lattice's unique properties and gain insights into the world of solid structures. So, let's continue our journey and unlock the secrets held within these crystalline arrangements. Welcome back, everyone. Hello again, bright minds. Today, we're delving deeper into crystal lattices, and it's time to explore the differences between two-dimensional and three-dimensional lattices. Visualizing the structure of two-dimensional lattices is relatively simpler for us. Think of it as looking at a beautifully detailed painting that spans a flat canvas. In contrast, three-dimensional lattices are a bit more intricate to envision. Picture a sculpture that you can view from all angles. The complexity increases as we add that third dimension. While both two-dimensional and three-dimensional lattices have their own allure, we'll be focusing on two-dimensional ones for now to build a strong foundation for understanding. So, keep your curiosity alive as we move forward and unravel the captivating world of crystal lattice structures. Hello again, Welcome back, students. In our exploration of crystallography, we're diving deeper into the world of unit cell tiling, but this time in 2 dimensions. Imagine a jigsaw puzzle where the pieces are unit cells. These unit cells must fit together flawlessly, covering every nook and cranny of the lattice's area. The arrangement results in mesmerizing and regular patterns that repeat themselves. This tiling is essential to accurately represent the crystal lattice and the atomic arrangement within. Keep in mind that this concept applies to a flat surface, just like when you're solving a puzzle on a table. Now, let's transition to the fascinating realm of 3 dimensions. Welcome back, students. Hello again, students. Our journey through crystallography leads us to the captivating world of 3-dimensional unit cell stacking. Just as unit cells must fit together perfectly in 2 dimensions, in 3 dimensions they must stack on top of each other to fill all available space. Think of it as constructing a 3-dimensional puzzle, where each unit cell adds a new layer to the structure. This stacking creates the intricate 3-dimensional crystal lattice, which plays a pivotal role in understanding the properties of various materials. It's incredible how these tiny building blocks come together to form the larger crystal structure. Now, as we wrap up this part of our discussion, remember that unit cells are the foundation of crystallography, helping us unlock the secrets of material structures. Next, we'll venture into new territories of our academic exploration. Hello again, Good day, students. Today, we're venturing into the intriguing realm of 2-dimensional lattices and their building blocks, the unit cells. A unit cell is the smallest repeating structure within a lattice, and in this case, we're looking at lattices that exist in 2 dimensions. There are 5 fundamental shapes that these unit cells can take, which we'll delve into shortly. However, our primary focus today will be on the oblique lattice. In this type of lattice, something fascinating happens. The lattice vectors, which are essentially the building blocks of the lattice, have varying lengths. Moreover, the angle between these vectors, represented as g, can be of any size, leading to unit cells that are intriguingly shaped parallelograms. So, let's start by exploring the characteristics of these 5 unit cell shapes and then delve deeper into the world of the oblique lattice. Good day, student. Now, let's shift our focus to the captivating world of the oblique lattice. Within this lattice, things get really interesting. The lattice vectors, which essentially define the arrangement of points in the lattice, have distinct lengths. Moreover, the angle, g, between these vectors can be of any size, completely breaking away from the constraints of right angles. What this means is that the unit cell, which is the repeating structure of the lattice, takes on the shape of an arbitrarily sized parallelogram. This opens up a whole realm of unique geometric properties and challenges. Imagine the implications of having such flexibility in lattice arrangements. As we proceed, we'll uncover the intricacies and significance of the oblique lattice in various applications and contexts. Now, as we delve deeper into our study of the oblique lattice, let's explore its applications and the significance it holds in various fields. In the realm of crystallography, understanding the arrangement of atoms in crystalline structures is pivotal, and the oblique lattice provides us with valuable insights into these arrangements. Material scientists utilize the oblique lattice to tailor materials with specific properties, harnessing its unique characteristics to create novel substances with desired traits. Engineers benefit as well, as they can design structures that are optimized for their intended purposes, taking advantage of the flexibility in lattice arrangements. From aerospace to electronics, the oblique lattice finds its way into various industries, contributing to advancements in research and innovation. So, students, remember that even seemingly abstract concepts like lattice shapes have a tangible impact on the world around us. As we delve deeper, as we conclude today's exploration of 2-dimensional lattices and their unit cell shapes, I hope you're walking away with a newfound appreciation for the intricate world of lattice arrangements. We've journeyed through the 5 fundamental unit cell shapes and delved into the unique properties of the oblique lattice. From crystallography to engineering, we've seen how these lattice structures impact our lives in profound ways. Our journey into the world of lattices is far from over. In our next session, Get ready to analyze the role of lattice defects, and how they influence the overall lattice behavior. Until then, keep your curiosity alive and your minds engaged, as we continue our quest for knowledge, in the realm of materials, structures, and their fascinating properties. As we conclude, hello again, dear students. Our learning journey continues as we delve into the intriguing world of two-dimensional lattices and unit cells. Lattices, in simple terms, are repeating patterns that help us understand the arrangement of atoms or points in a crystalline structure. In the world of two dimensions, we have 5 primary lattice types. Each of these lattices possesses a primitive unit cell, which serves as the fundamental building block. We've shaded these primitive cells in blue on figure 12.4. Now, pay special attention to the rhombic lattice. This lattice has a unique centered rectangular unit cell shaded in green. Unlike the primitive rhombic cell, this centered cell accommodates 2 lattice points within it. This distinction is essential for understanding the arrangement of points within these lattices. Are you ready to explore even further? Let's move on. Hello again. Welcome to the captivating world of crystalline structures, dear students. Why are crystalline structures so significant? Well, they form the foundation for understanding the properties of various materials. Just like Lego bricks come together to build fantastic structures, unit cells serve as the building blocks of crystalline arrangements. These unit cells help us comprehend how atoms are packed within crystalline solids. There are different types of unit cells we need to explore. First, we have the primitive unit cell, which contains only one lattice point. Then comes the body-centered unit cell, accommodating lattice points at the corners and one in the center. Finally, the face-centered unit cell holds lattice points at its corners and in the center of each face. By understanding the arrangement of atoms within these unit cells, we unlock the secrets of material properties. Ready to dive deeper? Let's proceed. Welcome to the Good day, students. Today, we're delving into the captivating world of crystal structures in 3 dimensions. As we journey further into this topic, we'll explore the essential concepts that help us comprehend the intricacies of real crystals. Our journey starts with the fundamental idea that understanding crystals goes beyond just 2 dimensions. We need to consider 3 dimensions. This brings us to the concept of a 3-dimensional lattice, which is defined by 3 lattice vectors, A, B, and C. These vectors play a crucial role in defining the arrangement of atoms within a crystal. Now, picture this. The unit cell, which is the building block of a crystal lattice, is a parallelepiped. This might sound complex, but it's essentially a 6-sided figure with all its faces being parallelograms. The dimensions of the unit cell are determined by the lengths of its edges, A, B, and C, as well as the angles alpha, beta, and gamma between these edges. It's worth noting that there are 7 possible shapes for a 3-dimensional unit cell, each with its unique arrangement of edges and angles. Let's take a look at figure 12.6 to visualize this. Alright, buckle up, as we journey deeper into the world of crystal structures and the fascinating dimensions they unveil. Good day, Alright, students, let's focus our attention on the shapes that unit cells can take in 3 dimensions. As I mentioned earlier, there are 7 possible shapes for a 3-dimensional unit cell. These shapes vary in terms of how their edges and angles are arranged. Just like the diversity we find in nature, each of these unit cell shapes comes with its own unique arrangement. To help you visualize this better, take a look at the diagram on this topic, showcasing the visual representation of these 7 unit cell shapes. Now, let's move on to explore more intricacies that lie within the dimensions of crystal structures. Alright, welcome back, students. We're now going to dive deeper into the parameters that define a unit cell in 3 dimensions. These parameters are edge lengths and angles. The lengths of the unit cell's edges A, B, and C play a crucial role in determining various properties of the crystal. These properties include the density of the material, its mechanical strength, and even its thermal and electrical conductivity. But that's not all. The angles alpha, beta, and gamma between these edges are equally significant. They define the symmetry and arrangement of atoms within the crystal lattice. The combination of these parameters holds the key to understanding how crystals pack together and how their physical properties emerge. Think of it as a puzzle, where the pieces are the unit cell parameters, and the picture they create is the intricate world of crystal structure. Let's move forward and unravel more of this fascinating puzzle. Welcome back, students. Great job, everyone! Now, let's bring crystal structures to life through visualization. Visual tools play a crucial role in helping us understand the arrangement of atoms within a crystal lattice. Two common visualization methods are space-filling models and ball and stick models. In space-filling models, we depict atoms as spheres that fill the available space within the unit cell. This gives us a sense of how atoms are arranged and how they interact with each other. On the other hand, ball and stick models show atoms as spheres connected by sticks, representing the bonds between atoms. These models help us visualize the connectivity and relationships between atoms in the crystal lattice. Visualizing crystal structures not only aids our comprehension but also allows us to appreciate the intricate symmetry and organization that underlie these materials. As we move forward, keep in mind that these visual representations are like windows into the hidden world of crystals. Great job, everyone! Alright, students, we've covered a lot of ground today as we ventured into the realms of crystal structure. But our exploration doesn't end here. Crystallography, the study of crystal structure and properties, is a fascinating field that continues to evolve. Beyond just understanding unit cells and parameters, crystallography delves into crystal systems' 7 categories that group crystals based on their symmetry. The intricate relationships between these systems contribute to the unique properties of different materials. Keep in mind that crystals are not only captivating from a scientific perspective but also play a pivotal role in various industries. From electronics to materials science, crystals influence our technological advancements in profound ways. As technology advances, so do our crystallography techniques, allowing us to uncover even more about these mesmerizing structures. With that said, our journey through the dimensions of crystallography is just the beginning. Stay curious and keep exploring. Alright, Good day, students. Today, we're delving into the fascinating world of crystal structures and how they come to be. Just having a lattice isn't enough to define a crystal structure. To create a crystal structure, we need to connect atoms or groups of atoms with each point on the lattice. In the simplest scenario, the crystal structure comprises identical atoms, with each atom placed directly on a lattice point. When this occurs, the patterns of the crystal structure and the lattice align perfectly. This kind of structure is often seen in metallic elements, which we'll explore in section 12.2. But there's a key condition: only elements, where all atoms are identical, can have this type of structure. Compounds, on the other hand, even if we were to place atoms on every lattice point, wouldn't have identical points because the atoms themselves aren't all the same. Let's journey further to understand these concepts deeply. Good day, students. Welcome back, students. Now, let's dive deeper into the relationship between crystal structures and lattice points. Crystal structures are intricately linked to lattices. Each lattice point plays host to an atom or a group of atoms. This connection between lattice and atoms forms the foundation of crystal structures. Picture this. In the simplest scenario, you have identical atoms occupying lattice points. This leads to a seamless alignment between the crystal structure and the lattice pattern. It's like a beautifully choreographed dance where each step is in perfect harmony with the other. But, as we explore further, we'll encounter scenarios where this perfect alignment isn't as straightforward. Welcome back, students. Welcome to the next phase of our journey, eager learners. When we're dealing with compounds, the story takes a different turn. Crystal structures for compounds aren't as straightforward as those for elements. Why? Well, in compounds, you're dealing with a mix of different atoms. Even if we were to place an atom on every single lattice point, there wouldn't be uniformity because the atoms aren't all the same. This leads to a distinct lattice pattern that doesn't perfectly match the crystal structure. Imagine it like a patchwork quilt, where each patch is unique and adds to the overall beauty of the piece. As we explore further, you'll see the intriguing ways these complex structures come to life. Thank you for your attention. Welcome to the next. Hello, curious minds. Let's reflect on our journey through crystal structures. So far, we've learned that the magic of crystal structures comes from the delicate interplay between atoms and lattices. Identical atoms create a symphony of perfection when placed on lattice points, resulting in a breathtaking alignment between crystal structure and lattice pattern. But when it comes to compounds, the rules shift. Here, we're dealing with a medley of different atoms, and even if we put atoms on every lattice point, they won't form the same harmonious tune as identical atoms. This concept isn't just fascinating, it's crucial in fields like material science and chemistry, where understanding these structures unlocks incredible insights into the behavior of matter. Keep your curiosity alive as we continue our exploration into the world of crystal structures. Hello, curious. Hello again, dear students. Today, we're delving into the captivating realm of crystal structures and the intriguing concept of unit cells. Imagine a crystal as a vast arrangement of atoms, but here's the twist: these atoms don't perfectly align with the lattice points. Instead, we have what we call a motif, which is a group of atoms associated with each lattice point. This motif is nestled within a unit cell, a tiny repeating unit that's the building block of the entire crystal structure. Just like stacking bricks to build a wall, we repeat this unit cell over and over to create the crystal's intricate pattern. Visualize this process as we move on to the next topic. Hello again, dear. Alright, students, let's explore a fascinating example to grasp the concept better. Imagine a two-dimensional crystal formation. Our diagram shows how this occurs using a hexagonal unit cell and a motif of two carbon atoms. By repeating this unit cell, a mesmerizing structure emerges, an infinite two-dimensional honeycomb pattern. This remarkable structure is known as graphene. Yes, the very material that secured a Nobel Prize in Physics for its discoverers back in 2010. In graphene, each carbon atom forms covalent bonds with three neighboring carbon atoms, forming an endless network of interconnected hexagonal rings. Can you believe that such intricate structures can arise from the simple repetition of unit cells? Alright, welcome to the captivating world of graphene, students. This extraordinary material's discovery was so groundbreaking that it earned its discoverers the prestigious Nobel Prize in Physics in 2010. What makes graphene so special? Well, it's all in its hexagonal lattice structure. Within this lattice, each carbon atom forms covalent bonds with its three neighboring carbon atoms, creating an immensely strong and interconnected web. Now, prepare to be amazed. Graphene boasts exceptional properties. It conducts electricity and heat with unparalleled efficiency, showcasing its potential for advanced electronics and even energy storage. Moreover, it's incredibly strong and flexible, which means it has applications in various industries. Let's move forward to learn even more. Welcome back, dear students. In today's lecture, we're delving into the intriguing world of crystal structures and how they manifest unique characteristics. Our focus now shifts to graphene, a remarkable example that showcases two key attributes. As we examine the crystal structure of graphene, you'll notice an interesting departure from the conventional arrangement of atoms on lattice points. Unlike many structures we've discussed, graphene doesn't have atoms positioned directly on these lattice points. This nuance highlights a crucial aspect when building a structure. Understanding the precise location and orientation of atoms within the motif in relation to the lattice points is essential. This insight empowers us to comprehend the structure's overall formation. Now, let's delve into the second characteristic. In graphene, bonds can form between atoms in neighboring unit cells, and intriguingly, these bonds aren't necessarily aligned parallel to the lattice vectors. This flexibility in bond formation adds another layer of complexity and versatility to the structure. Imagine the intricate dance of atoms creating these connections. As we explore this, remember that crystal structures come in various forms, each with its distinct set of characteristics and behaviors. This understanding not only expands our knowledge but also lays the foundation for advancements in materials science and technology. Now, onward to our next lesson. Welcome back, students. Today, we're delving into a fascinating field known as X-ray diffraction and crystal structure analysis. In this process, a monochromatic X-ray beam is directed towards a crystal. As the X-rays interact with the crystal, they undergo a phenomenon called diffraction, resulting in the creation of an interference pattern. To gather more information, the crystal is rotated, generating multiple diffraction patterns. By meticulously analyzing these patterns, scientists can unravel the intricate positions of atoms within the crystal. This technique has revolutionized our understanding of atomic arrangements and their role in various materials. Now, let's continue our exploration into the intricate world of crystallography. Welcome back, students. Good day, students. Today's topic takes us into the intriguing realm of medical and dental applications, where a remarkable material called nitinol plays a pivotal role. Nitinol, a unique alloy of nickel and titanium, possesses a special property known as the shape memory effect. This characteristic allows it to remember and return to a specific shape upon the application of heat. Now, let's delve into a fascinating example involving nitinol's role in improving heart health. Good day, student. Our journey into the world of nitinol applications leads us to an area of critical importance: heart health. As we know, heart conditions and blockages can severely impact blood flow. This is where nitinol stents step in as life-saving tools. Stents are small, expandable tubes used to open up blocked or narrowed arteries. Nitinol's unique property of shape memory comes into play here. These stents can be pre-set into their open shape, and then cooled and compacted for insertion into a blocked coronary artery. Once inside the body, the stent warms up to body temperature, and the nitinol remembers its original shape, thus allowing for improved blood flow. Our journey into the world. Alright, students, let's take a moment to truly understand the magic behind nitinol's shape memory effect. This phenomenon occurs due to the material's ability to transition between two distinct phases, austenite and martensite. At lower temperatures, nitinol adopts the martensite phase, which allows it to be easily deformed. However, when heated to a specific temperature, usually around body temperature, it transforms into the austenite phase, reverting to its original shape. This ability to remember and return to its shape makes nitinol incredibly valuable in various applications, including the field of medicine. Alright, students. Let's zoom back into the nitinol stent's role in improving blood flow. With the shape memory effect of nitinol, these stents can be precisely positioned and then expand to their intended shape once inside the body. This restoration of blood flow is a crucial step in treating heart conditions. Additionally, nitinol's properties offer advantages over traditional stent materials. The flexibility and biocompatibility of nitinol reduce the risk of complications and enhance patient comfort. This makes it an ideal choice for medical interventions requiring precision and adaptability. Let's zoom back. As we conclude our exploration of nitinol's applications, remember that its influence extends beyond just stents. In the world of dentistry and medicine, nitinol finds its place in various forms. Orthodontic wires and dental archwires, for instance, harness its flexibility and shape memory properties to create more comfortable and effective treatments. Additionally, nitinol's use as guide wires enables minimally invasive procedures, reducing patient discomfort and recovery time. It's truly remarkable how one material can contribute so significantly to the advancement of medical and dental practices. This wraps up our discussion on nitinol's versatile role in improving healthcare outcomes. As we Good day, students. Welcome to this fascinating section where we'll explore the world of metal structures and their remarkable properties. By the end of this session, you'll gain the ability to not only describe the lattice structure of metals and alloys but also connect the dots between the physical characteristics of metals and the types of bonding they possess. Let's jump right into it. Good day, student. You're doing wonderfully, students. Before we conclude, let's reflect on how the concept of unit cells intertwines with the properties of crystals. The size and arrangement of unit cells have a direct impact on a crystal's characteristics. Think of it like the arrangement of ingredients in a recipe affecting the taste of the final dish. Different unit cell sizes and arrangements lead to varying properties such as optical, electrical, and mechanical traits. As we bid farewell to this topic, remember that our exploration of unit cells and crystal lattices is a stepping stone into the captivating realm of materials science and the intriguing world of solid-state structures. You're doing wonderful. Fasten your seatbelts, because now we're about to link the lattice structure to the captivating physical properties of metals. The unique bonding in metals, known as metallic bonding, gives rise to some incredible traits. Have you ever wondered why metals are great conductors of electricity and heat? It's because they have these free-roaming electrons within their lattice that can easily carry energy. And that's not all. The malleability and ductility of metals can be attributed to their crystalline arrangement, allowing layers to topic past each other. Oh, and that shine you see on metal surfaces? It's all thanks to those free electrons that absorb and emit light. Cool, isn't it? Fasten your seat. Hello again, dear students. Today, we're unraveling the mysteries of metallic bonding in metals. Imagine a substance composed entirely of metal atoms. We call these metallic solids. The intrigue begins when we notice that the bond holding these metal atoms together isn't quite like what we've seen before. Unlike dispersion forces, which are too weak, and covalent bonds, which require more valence electrons than present, metals showcase something unique: metallic bonding. So, what's this all about? The valence electrons, those outer shell electrons that play a key role in bonding, are not confined to specific atoms or bonds in metals. Instead, they're like free spirits, spread throughout the entire solid, forming what we call a sea of electrons. Visualize this: a lattice of positive ions floating within this electron sea. This arrangement is what gives metals their distinctive properties and strength. Now, let's dig deeper into the mechanics of this intriguing metallic bonding phenomenon. Hello again, dear. Welcome to Topic 3, where we'll delve into the heart of metallic bonding, the delocalization of valence electrons. But before we proceed, let's remind ourselves what valence electrons are. They're those electrons residing in the outermost shell of an atom, determining its reactivity and bonding behavior. Now, in metallic solids, these valence electrons exhibit an extraordinary behavior. They become delocalized. What does that mean? Imagine these electrons not being tied down to specific atoms. They roam freely, forming that unique electron sea we discussed earlier. This electron sea isn't bound by atom-to-atom connections. Instead, it's a collective pool that surrounds the lattice of positively charged ions. This electron sea plays a pivotal role in the properties we associate with metals, like their electrical conductivity and malleability. It's like a shared resource that every positive ion taps into. Intriguing, isn't it? Let's press on. Welcome to Hello, inquisitive minds. Now that we've got a grip on delocalized valence electrons and the fascinating electron sea, let's explore the remarkable properties that stem from metallic bonding. First, we have electrical conductivity. Thanks to the free movement of those valence electrons throughout the solid, metals are excellent conductors of electricity. This shared electron sea allows electric current to flow with ease. But that's not all. Thermal conductivity, the ability to transfer heat, also shines in metals due to this electron sea's mobility. Now, here's something intriguing. Metals can be shaped and flattened without shattering. That's malleability and ductility for you. This remarkable feature arises from the malleable nature of the electron sea, allowing layers of ions to topic past each other. And let's not forget the sparkle. Metals' luster and reflectivity are a result of their densely packed structure and the way light interacts with their free electrons. Last but not least, their toughness is evident in their high melting and boiling points. These properties paint a vivid picture of the exceptional behavior that stems from the magical world of metallic bonding. Ready for more? Let's continue. Hello. Bravo, my diligent learners. As we wrap up our exploration of metallic bonding, let's take a moment to consider the real-world impact of this phenomenon. The properties we've uncovered today aren't just theoretical curiosities, they shape our world. Think about it. The electrical wires that power your gadgets, the shiny surfaces of vehicles, the structural integrity of bridges and skyscrapers, all owe their existence to metallic bonding. Industries rely on these properties for various applications. Moreover, materials science has pushed the boundaries of what we can achieve with metals, leading to advancements in aerospace, medicine, and countless other fields. But there's more depth to explore. The concept of the electron not only underpins these properties, but also gives us insights into alloy formation combining different metals to fine-tune their properties. Our journey into the world of metallic bonding has been illuminating, hasn't it? Remember, the more you understand about the inner workings of materials, the more empowered you become to shape the future. Keep that curiosity burning bright, and I can't wait to see you next time for another exciting exploration. Bravo, my. As we explore metallic properties further, one intriguing characteristic you might have noticed is the shine or luster on a clean metal surface. This luster is a direct reflection of the material's chemical bonding structure. When light interacts with the metal's surface, it reflects in a way that gives metals their unique sheen. Moreover, when you touch metals, you might have experienced a distinct cold sensation. This sensation is linked to metals' remarkable ability to conduct heat, known as thermal conductivity. The high thermal conductivity of metals means they can quickly transfer heat, making them feel cold to the touch. Let's move on to our next point. As we explore. Alright, students, let's talk about another extraordinary property of metals, their outstanding electrical conductivity. Metals allow electrically charged particles to flow through them with incredible ease. This property is a result of the way metal atoms are arranged and bonded together. When we delve into the structure of metallic bonding, we find that it facilitates the movement of electrons, which are responsible for electrical conduction. This seamless flow of charged particles makes metals essential for numerous applications in our modern world. Alright, now, let's explore an interesting correlation between two types of conductivity, thermal and electrical. It turns out that the thermal conductivity of a metal often goes hand in hand with its electrical conductivity. This means that metals with excellent electrical conductivity also tend to have high thermal conductivity. Take silver and copper, for instance. These elements showcase the highest electrical conductivities among all elements, and they also possess the highest thermal conductivities. This connection arises from the way metal atoms interact at the atomic level, creating an environment that supports both types of energy transfer. Now, as we wrap up our discussion, let's reflect on the profound relationship between chemical bonding and the captivating properties of metals. The way metal atoms bond and arrange themselves influences the overall behavior of the material. Remember, all forms of energy can be categorized as either kinetic or potential energy. In the realm of chemical reactions, potential energy changes play a crucial role. These changes arise from the electrostatic interactions that take place at the atomic level. So, when you hold that piece of metal, when you observe its luster, feel its coolness, or witness its exceptional conductivity, remember that these properties are a direct result of the intricate dance of atoms and their bonds. Thank you for joining me on this journey through metallic properties and chemical bonding. As we wrap up. Hello again, eager minds. Today, we're delving into the intriguing properties of metals that make them stand out. Our focus now shifts to malleability and ductility, two remarkable traits that set metals apart. Imagine being able to reshape a metal into a thin sheet or draw it into a wire without breaking it. That's exactly what malleability and ductility allow metals to do. Picture a metal sheet being expertly hammered into a delicate thinness or a wire being gently drawn to create a fine strand. These properties hint at something fascinating: the atoms within metals have a unique ability. They can actually slip past one another, like a well-coordinated dance, contributing to the material's flexibility. Now, you might wonder if all substances possess these characteristics. Well, the answer is no. Ionic and covalent network solids, for instance, behave quite differently. They tend to be brittle, lacking the ability to undergo such graceful transformations. So, remember, the next time you see a metal sheet or wire, you're witnessing the incredible result of atoms that are skilled at moving in harmony. Hello again. Greetings, young scholars. Let's dive a bit deeper into the inner workings of metals, shall we? We've discussed how metals possess the incredible ability to be malleable and ductile due to the mobility of their atoms. But how does this atom movement actually occur? Well, picture this. The atoms in metals are arranged in layers, forming what we call a lattice structure. These layers are like a stack of playing cards, they're not rigidly attached. When a force is applied, like when you hammer a metal sheet, the layers of atoms can shift and topic past one another. It's like a group of dancers performing a synchronized routine. They can adjust their positions without losing harmony. This atom mobility is a key reason why metals can be reshaped without breaking. So, next time you marvel at a metal's flexibility, remember that it's all thanks to the coordinated movement of atoms within those layers. Greetings, young. Welcome back, curious minds. Today, let's further unravel the mysteries of metals and their remarkable properties. We've learned how atom mobility plays a crucial role in making metals malleable and ductile. But what keeps these atoms together while allowing them to move so gracefully? The answer lies in something called metallic bonds. Imagine a sea of electrons surrounding the metal atoms. These electrons are shared among the atoms, creating a strong bond that holds them together. This bond is unique, it's not localized between specific pairs of atoms like in covalent bonds. Instead, it's a communal sharing of electrons, creating a cohesive force within the metal structure. This electron sea model beautifully explains the behavior of metal atoms. They're like participants in an intricate dance, held together by the rhythm of metallic bonds, allowing them to move and shift without losing their connection. So, remember, the next time you witness the elegance of a metal being shaped, you're witnessing the interplay of atoms and their electron sea. Thank you for exploring this fascinating world with me. Class dismissed. Welcome back. Welcome, students. Today, we're delving into the fascinating world of crystal structures found in metallic solids. These structures play a crucial role in determining the properties and behavior of metals. Imagine these structures as intricate patterns where atoms are meticulously arranged. Let's start by discussing the basic concept of crystal structures and how they relate to metals. Welcome, student. Now, let's explore the first type of cubic lattice, the primitive cubic structure. This arrangement is quite rare in metals, with only a few examples like the radioactive element polonium. In this structure, each lattice point holds a single atom. Imagine it as a simple and straightforward pattern, but it's a rarity in the world of metals. Next up, we have the face-centered cubic structure. This arrangement is quite significant, and you'll find it in various common metals. In this structure, atoms are positioned at the corners and the center of each face of the cube. This arrangement results in a tightly packed lattice. Noteworthy metals adopting this structure include aluminum, lead, copper, silver, and gold. Next up, as we wrap up our exploration of metallic crystal structures, it's crucial to understand their impact on the properties of metals. The arrangement of atoms within these structures influences various aspects, including mechanical strength, electrical conductivity, and thermal behavior. Remember, the way atoms are packed contributes to the characteristics we observe in different metals. This concludes our discussion for today. Keep delving into the exciting world of material science. As we wrap up our Good day, students. In today's lesson, we'll delve into the intriguing concept of unit cells and how atoms are distributed within them. As we observe Figure 12.11, you'll notice something interesting in the bottom row. Atoms situated on the corners and faces of a unit cell aren't completely contained within that cell. Instead, they're shared with neighboring unit cells. Take the corner atom, for instance, it's shared among 8 unit cells. This means that only a fraction, specifically 1/8, of the atom resides within a particular unit cell. Picture a cube with 8 corners. Each primitive cubic unit cell contains one atom, given that 1/8 of the atom exists within it, as demonstrated in Figure 12.12. Now, let's move on and explore more about atom distribution in different types of unit cells. Good day, students. Continuing our journey, let's take a closer look at the various types of unit cells. Specifically, we'll focus on the body-centered cubic unit cell, as shown in Figure 12.12. B. This type of unit cell contains two atoms. Here's the breakdown. One atom sits at a corner, just like in the primitive cubic unit cell, and another atom rests at the center of the unit cell. Again, we find that 1/8 of the corner atom's contribution adds up to 1 atom, and the center atom is fully contained within the unit cell. The intriguing arrangements of atoms within these unit cells contribute to the overall structure of materials. Now, let's move forward and explore yet another type of unit cell. Continuing our journey, get ready to uncover another type of unit cell, the face-centered cubic unit cell. This cell is quite fascinating due to its atom distribution. In materials like face-centered cubic metals, atoms actually lie on the faces of the unit cell. However, these atoms are shared by two neighboring unit cells. This sharing means that each unit cell only holds a fraction of the atom's presence, in this case, 1/2 of the atom. If we break down the composition, a face-centered cubic unit cell, as depicted in Figure 12.12, c, accommodates 4 atoms. 1 atom comes from the corners, making up a full atom due to the 1/8 contribution, and 3 atoms are derived from the faces, with each face atom contributing 1/2 to the unit cell. This intricate arrangement is essential to understanding the properties and behaviors of materials. Now, let's dive even deeper into this captivating subject. Get ready to uncover. Before we wrap up today's lesson, let's consolidate our understanding of fractional atom distribution within unit cells. It's crucial to recognize that the fractional contribution of each atom depends on its specific location within the unit cell. As you can see in Table 12.1, the fractional parts vary based on whether the atom is on a corner, face, or center. This understanding plays a significant role in determining the overall structure and properties of materials. Our exploration today has shed light on how atoms are arranged in unit cells, sharing their presence with neighboring cells and contributing to the incredible diversity of materials we encounter in our everyday lives. As we move forward in our studies, keep in mind the intricate connections between atomic arrangement and material behavior. Thank you for your attention, and I look forward to our next lesson. Before we wrap, good day, students. Today, we're delving into the fascinating topic of close packing of atoms in metals. To kick things off, let's talk about valence electrons and how their collective sharing creates favorable conditions for atoms in metals to closely pack together. Now, imagine atoms as spheres, and this concept will help us grasp the structures of metals. In a two-dimensional arrangement, the most efficient way to pack equal-sized spheres is by surrounding each sphere with 6 neighbors, forming a hexagonal pattern, as you can see at the top of Figure 12.13. But we're not done there. To truly understand the three-dimensional structure, we need to stack additional layers on top of this base layer. And here's the catch. For optimal packing efficiency, the spheres in the second layer must fit into the depressions or gaps of the first layer. This intricate arrangement is what allows metals to achieve their unique properties. Let's move forward to explore more about close packing and its implications. Good day, students. Hello, dear students. Today, we're going to dive into the intriguing world of close packing of spheres and explore the placement possibilities for the third layer. This is a fascinating concept in the realm of crystallography and atomic arrangements. Imagine you have a stack of spheres, and we're considering where to place the third layer. We have 2 exciting choices to explore. Choice number 1 involves placing the third layer of spheres directly in the depressions that align with the spheres in the first layer. You can see this concept visualized on the left-hand side of Figure 12.13. The dashed red lines in the side view show how this arrangement works. If we continue this pattern, the fourth layer would then fit right over the spheres in the second layer, resulting in what we call an above stacking pattern. This specific arrangement is known as hexagonal close packing or HCP. Now, let's move on to choice number 2. In this scenario, the third layer spheres would be positioned directly over the depressions that were marked with red dots in the first layer. This presents an interesting alternative that can lead to distinct atomic arrangements. As we explore these options, keep in mind the significance of close packing and how it relates to the arrangement of atoms and molecules in various materials. The spatial arrangement of particles has profound implications for the properties and behaviors of substances. So, let's continue our journey into the fascinating world of crystal structures and atomic arrangements. Hello, dear Welcome, dear students. In today's lesson, we're delving into the intricate world of crystal structures, focusing specifically on the hexagonal close-packed arrangement. So, what exactly is the hexagonal close-packed structure? It's a fascinating arrangement commonly found in metals. Imagine a lattice that's made up of layers. In this structure, each primitive hexagonal unit cell contains not one, but two atoms. One atom is derived from each layer. But here's the catch. These atoms aren't directly on the lattice points located at the corners of the unit cell. This brings us to an interesting stacking sequence known as a bob. This sequence refers to the arrangement of layers, where the first layer is followed by the second, and then it repeats, a bob. Let's move forward and explore more about this intriguing structure. Welcome, dear Hello again, students. Let's dive deeper into the configuration of the hexagonal close-packed structure. As I mentioned earlier, this structure is special because each primitive hexagonal unit cell holds not just one, but two atoms. These atoms come from different layers within the lattice. This arrangement plays a crucial role in determining various material properties. Understanding how atoms are positioned within the unit cell is key to comprehending how the material behaves under different conditions. So, remember, the arrangement of these atoms has a significant impact on the overall characteristics of the material. Hello again. Great job keeping up, students. Now, let's explore the intriguing relationship between atom positions and lattice points in the hexagonal close-packed structure. You see, the atoms don't align precisely with the lattice points, which are situated at the corners of the unit cell. This leads to a unique geometric arrangement that influences the properties of the material. The atom's positioning in relation to the lattice points determines how they interact with neighboring atoms and, consequently, how the material behaves. It's like a puzzle where every piece has its place and purpose. So, remember, these atomic positions are the building blocks of the material's properties. Great job keeping up. Excellent progress, students. Let's zoom in on the above stacking sequence that characterizes the hexagonal close-packed structure. This sequence refers to the alternating arrangement of layers within the lattice. The first layer is followed by the second, then the first again, and so on. This arrangement has significant consequences for the material's stability and properties. It influences how the atoms interact across layers and contributes to the overall strength and behavior of the material. Remember, this sequence is like the rhythm that governs the dance of atoms in the lattice, determining the material's structural harmony. Excellent. Welcome back, everyone. Let's dive deeper into the structure of cubic close packing and its layers. As we've discussed, cubic close packing has a surprising similarity to the face-centered cubic unit cell. The arrangement of layers plays a crucial role here. The layers are stacked using ABC layer stacking, and this stacking pattern is integral to the crystal structure. Now, visualize this. When we refer to figure 12.14b, we can clearly see how these layers are positioned in relation to the body diagonal of the cubic unit cell. It's like putting together a complex puzzle, isn't it? This understanding brings us closer to unraveling the mysteries of crystal packing. Welcome back, everyone. Fantastic to have you all here today. Now, let's explore why understanding cubic close packing and crystal packing structures is so important. These arrangements might seem abstract, but they have real-world implications. Crystal packing structures play a vital role in determining the properties of materials. From strength to conductivity, these structures influence it all. Think about it. The relation between cubic close packing and the face-centered cubic unit cell we've covered earlier is like a cornerstone. It helps us lay the foundation for understanding advanced materials. So, when you look at materials with cubic close packing, remember that their properties are intricately tied to the arrangement we're discussing. Ready to uncover even more? Fantastic to have you. Hello, dear students. Today, we're delving into the world of alloys, fascinating materials that combine the characteristics of metals. An alloy is essentially a substance containing more than one element, and it behaves like a metal. You might be wondering, why is this important? Well, alloying metals is a key way to change and enhance the properties of pure metallic elements. Think about iron, for instance. Most of its common applications involve using alloy compositions, like stainless steel. Now, let's explore the intriguing process of alloying and its impact on various materials. Hello again, bright minds. Let's explore some specific examples of alloys that you might come across. We have bronze, which is created by combining copper and tin. This alloy has been used for ages to craft things like statues and tools due to its enhanced properties. Then there's brass, a blend of copper and zinc, often used for decorative items and musical instruments. Even gold gets in on the alloy action. Pure gold is too soft for jewelry, so we mix it with other metals to create more durable and attractive alloys. And who could forget stainless steel? It's a real workhorse, made by alloying iron with chromium and other elements to create a corrosion-resistant material used in countless applications. Hello again. Greetings, inquisitive minds. In our journey through alloys, we mustn't overlook the wide array of alloys out there. Our trusty Table 12.2 sheds light on some of these alloys and what they're made of. As you'll see, each alloy has a distinct composition that grants it specific traits. From aluminum alloys used in aircraft to nickel-based superalloys used in extreme conditions, alloys truly come in all shapes and sizes. This incredible diversity is what makes them such versatile and valuable materials in our world. Greetings. Welcome back, students. Today, we're delving into the intriguing realm of substitutional alloys and their formation. These alloys arise when two metallic components possess similarities in both atomic radii and chemical bonding characteristics. This shared nature allows them to coexist in a unified structure. Take, for instance, silver and gold, a perfect example of such an alloy. Their atomic radii and bonding characteristics align seamlessly, resulting in a homogeneous alloy that spans the entire composition range. Now, remember, the key here is the compatibility of atomic sizes and bonding tendencies. However, don't forget that not all metals can readily form these alloys. When the atomic radii of two metals differ by more than approximately 15%, their solubility becomes notably limited. Let's explore this fascinating topic further. Welcome back, students. Greetings, students. Today, our focus is on the fundamental connection between atomic radii and the formation of substitutional alloys. A crucial aspect for these alloys to emerge is the resemblance in atomic sizes between the constituent metals. Imagine a puzzle where the pieces fit seamlessly together. That's what happens when atoms with similar radii come together in an alloy. Visualize a metallic lattice with atoms occupying specific positions, forming a unified structure. When the atomic radii of the metals vary by more than about 15%, the compatibility starts to waver. This can lead to limitations in the solubility of these metals in each other, hindering the formation of a complete alloy. Stay curious as we proceed to delve even deeper. Greetings, students. Hello, dear students. Today, we're delving into the fascinating realm of interstitial alloys. These alloys are a result of some intriguing atomic interactions. To create an interstitial alloy, we need to ensure that the solute atoms have a significantly smaller bonding atomic radius than the solvent atoms. This arrangement paves the way for a unique type of alloy formation. In many cases, the interstitial element introduced is a nonmetal that forms covalent bonds with the neighboring metal atoms. Now, this addition of interstitial components brings about some remarkable changes in the properties of the metal lattice. Brace yourselves for this. The metal lattice becomes harder, stronger, and less ductile. A classic example we encounter is steel. We all know iron, right? Well, steel, which is an alloy of iron containing around 3% carbon, is much tougher and more robust than pure iron. But it doesn't stop there. Alloying elements like vanadium and chromium can be incorporated to boost strength, enhance fatigue resistance, and even combat corrosion. As we journey through this topic, keep in mind the interplay between atomic radii, bonding, and how these interactions sculpt the characteristics of materials. Let's move forward and explore this captivating world of interstitial alloys. Hello, dear Greetings, students. Today, we're shining a spotlight on the remarkable properties of stainless steel, specifically thanks to the inclusion of chromium. The magic here lies in chromium's ability to create a protective shield. When chromium is present, it forms a passive oxide layer on the surface of the steel. This layer acts as a barrier, shielding the underlying material from the corrosive effects of the environment. This unique trait gives stainless steel its name, stainless, as it resists rust and deterioration, making it an ideal choice for various applications. Let's continue exploring the fascinating attributes of stainless steel. Greetings, students. Welcome back, dear students. Our exploration of stainless steel continues as we turn our attention to another essential element, nickel. Nickel's presence within stainless steel brings about some fantastic enhancements. Notably, it improves the steel's toughness and ductility, making it more resistant to breaking or deformation. Moreover, nickel's role in stainless steel grants it the ability to withstand extreme temperatures without losing its structural integrity. This attribute is especially critical in environments where temperature fluctuations are a common occurrence. So, as you can see, the synergy of elements within stainless steel produces materials that can withstand a multitude of challenges. Welcome back. Hello, bright minds. As we proceed through our journey into the world of stainless steel, let's discuss how the variation in element ratios leads to the impressive versatility of this material. By adjusting the composition of carbon, chromium, and nickel, engineers and scientists can fine-tune the properties of stainless steel. This means that stainless steel can be tailored to possess specific attributes like strength, corrosion resistance, and even electrical conductivity. Understanding these compositions becomes crucial when choosing the right material for various applications. And that concludes our exploration of the captivating realm of stainless steel and its alloyed elements. Stay curious and eager to learn, my dear students. Hello, bright minds. Hello there, students. Today, we're delving into the intriguing realm of heterogeneous alloys and how their composition influences their properties. So, what exactly are heterogeneous alloys? Well, these are alloys where the components aren't uniformly distributed throughout the material. A fantastic example of this is the pearlite alloy, which contains two distinct phases. Imagine these phases as separate entities coexisting within the alloy. One phase consists of almost pure body-centered cubic iron, while the other is the compound Fe3C, also known as cementite. Let's move on to the next topic to explore how these distinct phases affect the properties of such alloys. Hello there, student. Now, let's uncover the hidden secrets of properties. When we talk about rapidly cooled alloys, we're looking at increased hardness but decreased ductility. In simpler terms, these alloys are tough, but they're not as flexible. Slow-cooled alloys, however, show a different story. They're tougher and more ductile. Picture a slow-cooled alloy like a well-organized team. They're tough and they can handle various situations gracefully. These property variations are more than just scientific quirks. They play a crucial role in deciding how these alloys can be used in various applications. Moving on, let's continue our exploration of the intricate world of alloy properties. Now, as we wrap up our discussion, let's recap what we've learned about heterogeneous alloys. We saw that their composition and the way they're formed significantly influence their properties. Remember, alloys formed through rapid cooling are tough yet less flexible, while those formed through slow cooling are both tough and ductile. Now, why does all of this matter? Understanding these property variations allows engineers and scientists to create alloys tailored for specific purposes. Imagine the possibilities. From sturdy yet brittle alloys for certain applications to tough and malleable alloys for others. So, my dear students, I encourage you to explore further into this captivating realm. Who knows, you might just be the ones revolutionizing the alloys of the future. Keep those curious minds engaged, and remember, science is an adventure waiting to be explored. Until next time, as we wrap. Hello there, students. Today, we're delving into the captivating realm of heterogeneous alloys and how their composition plays a pivotal role in determining their properties. Heterogeneous alloys, as the name suggests, are alloys where the components are not uniformly dispersed. Our focus turns to an intriguing example called pearlite. This alloy is truly a marvel, composed of two distinct phases. One of these phases showcases pure body-centered cubic iron, while the other reveals the presence of a compound known as Fe3C, or cementite. Picture it like a blend of different elements coming together in a non-uniform manner. Now, let's move forward to discover how the composition and formation process impact the properties of these alloys. Hello there, student. Alright, dear students, let's uncover the factors that shape the properties of heterogeneous alloys. Remember, it's not just about what these alloys are made of, but also how they're formed. Imagine two scenarios, one where we rapidly cool a molten mixture, and another where we allow the same mixture to cool slowly. The magic lies in the differences we observe. Heterogeneous alloys formed through rapid cooling exhibit unique properties, distinct from those formed through slow cooling. The pace at which these alloys solidify greatly influences their final characteristics. So, whether it's quick cooling or a more patient approach, the resulting properties of the alloy are bound to vary. Isn't that fascinating? Alright, dear. Hello again, my eager learners. Our journey through the world of heterogeneous alloys continues. Today, we're peeling back the layers to uncover the various pathways that lead to the unique properties of these alloys. Remember, it's not just one factor that calls the shots, it's a combination of elements at play. The composition of the alloy, the rate at which it solidifies, these elements hold the key. Microstructure, the tiny arrangement of atoms, has a profound impact on the alloy's properties. Think of it as a puzzle where every piece matters, and the final picture is the alloy's behavior and characteristics. Stay with me as we venture deeper into the intricacies of these alloys. Hello again, my good day, students. Today, we're delving into the fascinating realm of intermetallic compounds. Unlike mixtures, intermetallic compounds are well-defined compounds, which means they possess specific properties and their composition cannot be altered. One intriguing characteristic of these compounds is the ordered arrangement of different types of atoms within them. This ordered structure leads to remarkable advantages, such as enhanced structural stability and higher melting points compared to the individual metals that make them up. These qualities make intermetallic compounds highly appealing for applications requiring high temperatures. However, as we explore further, we'll also learn about their limitations. Let's move on to our next topic to understand more about the unique properties of intermetallic compounds. Good day, student. Welcome back, students. Now, let's take a closer look at the arrangement of atoms in intermetallic compounds. Unlike the random distribution of atoms in alloys, intermetallic compounds feature an ordered arrangement of atoms. This ordering contributes significantly to their structural stability and improved properties. Just imagine atoms aligning in an organized fashion, creating a strong and predictable structure. This is one of the factors that contribute to their impressive performance, especially at elevated temperatures. As we proceed, we'll delve deeper into the advantages of this unique arrangement. Welcome back, students. Great to have you with us, students. Our exploration of intermetallic compounds continues. The ordered atomic arrangement we discussed earlier leads to some remarkable enhancements in their properties. This includes exceptional structural stability, which arises from the atom's organized alignment. Additionally, intermetallic compounds tend to exhibit higher melting points when compared to the individual metals that form them. This makes them particularly well suited for applications that involve high temperatures. Imagine the potential of materials that can withstand extreme heat while maintaining their structural integrity. As we progress, we'll also uncover some of the challenges associated with these compounds. Great to have you with us. Welcome to our final topic, students. Let's summarize our journey through the world of intermetallic compounds. We learned that these compounds offer distinct properties due to their ordered atomic arrangement, leading to enhanced structural stability and higher melting points. This makes them valuable contenders for applications involving extreme heat. However, their brittleness poses a challenge that needs to be carefully considered. As budding scientists, it's crucial to grasp the balance between advantages and limitations when working with innovative materials like intermetallic compounds. With this knowledge in hand, you're better equipped to explore the ever-evolving landscape of materials science. Keep your curiosity alive and continue to unravel the mysteries of the natural world. Thank you for joining me in this enlightening exploration. Welcome to our final. Hello, dear students. Today, we're delving into a captivating realm of materials known as intermetallic compounds. These compounds play crucial roles in our modern society, contributing to various industries. Let's start by understanding the significance of Ni3Al. This intermetallic compound is a key component in jet aircraft engines due to its remarkable strength at high temperatures and its low density. Can you imagine the power of materials that can withstand extreme conditions and yet remain lightweight? Now, let's move on to our next fascinating example. Hello, dear. Welcome back, students. Our journey through the world of intermetallic compounds continues with an example that impacts our everyday lives. Have you ever wondered why some razor blades stay sharp for longer periods? It's all thanks to the compound Cre3Pt. Razor blades are coated with this intermetallic compound to enhance their hardness, allowing them to maintain their sharpness over time. Imagine the convenience and efficiency this brings to our daily routines. Now, let's move forward to explore another intriguing application. Welcome back, students. Hello again, curious minds. Our next stop on this intermetallic journey brings us to a realm of amazing physics: superconductivity. Imagine a substance that conducts electricity without any resistance when cooled below a critical temperature. That's what Nb3Sn is, a superconductor. This incredible property has significant applications, such as in the magnets of MRI scanners, which play a vital role in medical imaging. However, there's a catch. We have to maintain these magnets at extremely low temperatures, making MRI devices costly to operate. But the benefits are immense. Now, let's uncover another remarkable use of intermetallic compounds. Hello again, greetings, knowledge seekers. Our exploration of intermetallic compounds wouldn't be complete without discussing their role in crafting magnets. Enter SmCO5. A hexagonal intermetallic compound that's used to create permanent magnets. These magnets find their way into lightweight headsets and high-fidelity speakers, enriching our auditory experiences. The ability of intermetallic compounds to shape our technologies is truly mesmerizing. But our journey isn't over just yet. Greetings. Welcome back, students. In this part of our journey, we're going to explore the fascinating world of chemical bonding among the elements of the third period in the periodic table. We'll see how these elements come together to form various compounds through their valence electrons. Now, let's delve into the details. Welcome back, students. As we venture into the world of chemical bonding, we encounter the element argon, which possesses a rather intriguing behavior. With its 8 valence electrons, argon achieves a complete octet, making its electron configuration highly stable. Interestingly, this stability prevents argon from forming any bonds. Unlike its neighboring elements, argon stands alone in its lack of chemical reactivity. As we venture into Now, let's turn our attention to chlorine, sulfur, and phosphorus, each of which displays distinct bonding behavior. Chlorine pairs up to create molecules like 1Cl, where a single bond holds the atoms together. Sulfur, on the other hand, goes a step further, forming S molecules held together by 2 bonds. Phosphorus takes this bonding game even higher, creating P molecules with 3 bonds. These different bonding patterns result in unique molecular structures. Now, let's turn. Moving forward, we encounter silicon, an element that takes bonding to another level. Silicon forms an extended network solid, where every silicon atom is intricately bonded to 4 neighboring atoms, all equidistant from each other. This results in the creation of a 3-dimensional lattice structure, setting silicon apart from the bonding behavior of other elements in the same period. Moving forward, as we ponder the patterns we've observed, it becomes clear that the octet rule plays a pivotal role in understanding chemical bonding among these elements. This rule explains how elements strive to achieve a stable configuration of 8 valence electrons. From chlorine to sulfur, phosphorus, and silicon, each element's bonding behavior can be attributed to its pursuit of this octet stability. As we conclude this part of our exploration, remember that chemical bonding is a complex dance among the third period elements. We've uncovered the mysteries behind argon's stable octet, the varied bonding tendencies of chlorine, sulfur, and phosphorus, and the exceptional network solid structure of silicon. All of these behaviors can be deciphered through the lens of the octet rule, providing us with a deeper appreciation for the intricacies of chemical interactions. As we conclude, bravo, students! We've journeyed through the world of chemical bonding among the third period elements. We've seen how argon's stable octet sets it apart, while chlorine, sulfur, and phosphorus form unique molecules with varying numbers of bonds. Silicon, on the other hand, captivates us with its extended network solid. And through it all, the octet rule has been our guiding light. But don't rest just yet. Our adventure in chemistry is far from over. Stay tuned for more exciting insights into the wonders of the molecular world. Bravo, student! Great job, students! Now that we've unraveled the bond types, let's see how they influence the properties we observe in solids. Ionic bonds, known for their electron transfer, contribute to solids with high melting points, due to the strong electrostatic attraction between ions. Covalent bonds, which involve shared electrons, result in solids with strong, directional bonds that lend them their hardness. Metallic bonds, with their sea of mobile electrons, lead to excellent electrical conductivity and malleability. As for intermolecular forces, these subtle interactions impact the volatility of molecular solids, affecting their phase transitions. It's truly mesmerizing to see how the atomic-level connections shape the macroscopic properties we observe. Let's keep our curiosity burning as we explore further. Great job, student! Alright, students, let's dive deeper into the mobility of those valence electrons in metals. Remember, these electrons are not tied down to specific metal ions. Instead, they're free to move throughout the metal structure, contributing to its unique properties. Now, here's where it gets fascinating. When we apply a voltage to a metal wire, something interesting happens. Those negatively charged electrons start flowing. Why? Well, they're moving from areas with higher electron density to areas with lower electron density. In other words, they're flowing toward the positively charged end of the wire. This flow of electrons is what we know as electric current. It's this movement of electrons that makes metals excellent conductors of electricity. Stay with me, because we're about to explore more captivating aspects of this model. Alright,